Module 4, Lecture A, Scaling Distributions. By the end of this lecture, you will be able to apply standard, min-max, max-absolute, robust, and sample normalization transformations. Compare quantile and power transformations for skewed numerical features. And choose scaling strategies that respect sparse and dense data constraints. Core scaling methods. Standard scaling. Standard scaling puts numerical features on a common scale without changing the overall shape of their distributions. It centers each feature around its average and measures values relative to how spread out that feature is, so typical values are near zero, higher values are positive, and lower values are negative. This is useful when features use different units, because it helps machine learning models compare them fairly instead of favoring larger numbers. Standard scaling puts values on a common scale so they can be compared more fairly. In data preprocessing, this is useful when features such as square footage and number of bedrooms have very different ranges, but both influence a prediction. Scaling helps algorithms like linear regression and support vector machines perform better, because distances and gradients are less likely to be dominated by one large-scale feature. With standard scaling, learn the average and spread only from the training data, then apply those same values to other datasets to avoid data leakage. It works best when features are fairly symmetric and not strongly affected by outliers. If extreme values are present, robust scaling may be a better choice. Standard scaling changes a feature's location and scale, but it does not remove outliers or make the data normally distributed. Python code. Standard scaling. Standard scaling transforms simple numeric features from their original units into standardized values. This makes the data centered around a mean of 0, with a spread of one standard unit, so features can be compared on a common scale. We import NumPy and pandas to work with numerical data and manipulate datasets. We also use Scikit-Learn StandardScaler to standardize features by centering them around the mean and scaling them to unit variance, which helps many machine learning algorithms perform better. We create a small pandas data frame with 5 home examples and 3 features: area, bedrooms, and distance. These features use different measurement scales, which sets up why standard scaling is needed. The code first verifies that the housing data has the expected size, 5 homes with 3 numeric features each. If the data does not match this structure, it raises an error. This early check helps ensure the data is valid before any further analysis or transformation begins. We use Scikit-Learn's StandardScaler to standardize the housing data. Its fit and transform process calculates each feature's mean and standard deviation, then rescales the values so each feature has a mean of 0 and a standard deviation of 1. This makes features with different units and scales easier to compare. We create a new pandas data frame to store the scaled values while keeping the same column names as the original housing data. This preserves the dataset structure and labels, making the scaled features easier to interpret. We first summarize the original dataset by calculating each feature's mean and standard deviation, then round the results for easier reading. We repeat the same summary after scaling to see how the transformation changed the data. The comparison shows that scaling centers the features around 0 and adjusts their spread to unit variance. The output first notes that the housing dataset contains features with different units and ranges, which explains why scaling may be needed. It then displays the original data rounded to 2 decimal places for readability, using a formatted text view that omits the index, so the focus stays on the feature values. The output notes that standard scaling centers the data near 0 by giving each feature a mean of 0 and a standard deviation of 1. The scaled values are then rounded to 2 decimal places and shown without row indices, making them easier to read and compare with the original data. We first introduce the original dataset's means and standard deviations to provide context. Then, the summary statistics are converted into a readable string, so the mean and standard deviation for each feature can be displayed clearly and compared with the scaled data later. The program displays a summary of the scaled data, showing each feature's mean and standard deviation. After standard scaling, the means should be close to 0, and the standard deviations close to 1. This check confirms that the scaling was applied correctly and that the features are on a consistent scale. This example shows how standard scaling makes features with different units, such as area, bedrooms, and distance, easier to compare. Using Scikit-Learn's StandardScaler, each feature is transformed, so its values are centered near 0 and have a standard deviation of 1. The before and after statistics confirm that the original data had different scales, while the scaled data has been successfully standardized. Min-max scaling. Min-max scaling converts numerical features to a common range, usually from 0 to 1. The smallest value becomes 0, the largest becomes 1, and all other values are placed proportionally between them. This helps machine learning models compare features with different units, such as apartment size, income, and commute time, without giving extra importance to features that simply have larger numbers. Min-max scaling changes the scale of data while preserving the shape of its original distribution and the relative spacing between values. This makes features easier to compare and helps prevent differences in units from distorting learning. It is especially useful for distance or gradient-based methods, such as nearest neighbor algorithms and neural networks, and for tasks like image processing or customer analytics, where values need to be on a consistent scale. Min-max scaling depends on the observed minimum and maximum, so extreme outliers can compress most values into a narrow range and hide important differences. It works best when those limits are stable and meaningful. Always fit the scaling on the training data only. Then apply the same scaling to other datasets. Used carefully, it puts features on a common range while preserving their order and proportions. Python code. Min-max scaling. This example shows min-max scaling, which transforms each feature so its values fall between 0 and 1. The scaled results keep the original ordering and relative spacing of the values. We import NumPy for numerical work, pandas for data handling, and the MinMaxScaler from Scikit-Learn for preprocessing. Together, these tools prepare the dataset for min-max scaling, which rescales feature values to a chosen range, usually from 0 to 1. We create a small, in-memory dataset with a pandas data frame, so it is easy to inspect and work with. The data includes 3 features: home size in square feet, income in dollars, and commute time in minutes. Each feature is stored as a list of values for later transformation and analysis. To prepare for scaling, calculate each feature's range by subtracting its minimum value from its maximum value. Then check whether any feature has a range of 0, meaning it has no variation. If so, raise an error, because scaling requires at least 2 different values to work correctly. MinMaxScaler from Scikit-Learn rescales each feature so its values fall between 0 and 1. Applying its fit-transform method finds the minimum and maximum for each feature, then adjusts the data to that range while preserving the original order and relative spacing of values. After scaling the data, we convert the transformed array back into a data frame using the original column labels. This keeps each feature clearly identified, making the scaled data easier to interpret and analyze. To compare original and scaled data side by side, add clear prefixes to each set of columns, such as raw for the original values and scaled for the transformed values. Then combine the two data tables horizontally, so matching features appear next to each other. This makes it easy to inspect how each value changed after scaling. The output explains that min-max scaling transforms each feature to a range from 0 to 1. It then compares the original and scaled data, rounded for readability. So the effect of scaling is easy to see. Finally, it shows the original minimum and maximum values learned for each feature. This script shows how min-max scaling converts features such as home size, income, and commute time to a common range from 0 to 1. It first checks that each feature has variation, then uses Scikit-Learn to learn each feature's minimum and maximum values and rescale the data. The output compares the original and scaled values and reports the learned ranges, making the scaling process easy to inspect. Max absolute scaling. Max absolute scaling rescales each numerical feature by dividing values by the largest absolute value in that feature. So results fall between -1 and +1, while keeping their signs. It is useful when both positive and negative values matter, such as profits and losses. Unlike standard scaling, it does not center the data. And unlike min-max scaling, it does not force the smallest value to 0. Max absolute scaling is useful for sparse datasets because it preserves 0 values while rescaling feature magnitudes. This makes it well-suited to text analysis, recommendation systems, and document term matrices, where most entries are 0. By avoiding mean subtraction, it helps maintain the data's sparse structure, saving memory and improving speed. Max absolute scaling puts features on a comparable scale while preserving positive, negative, and 0 values. Because it depends on the largest absolute value in each feature, extreme outliers can shrink the rest of the data and make differences harder to see. It works best when the maximum value is meaningful. Zeros should stay unchanged, and the sign of the data matters, but you should check for outliers first. Python code, max absolute scaling. Max absolute scaling rescales signed values by shrinking their magnitudes while keeping zeros unchanged and preserving whether each value is positive or negative. After scaling, compare the original and scaled feature ranges to see how the values have been compressed without changing their signs. We import NumPy and pandas for numerical work and data manipulation, along with the MaxAbsScaler from Scikit-Learn for scaling data. This scaler divides each column by its largest absolute value, keeping signs and zeros unchanged. These tools prepare the data for later scaling steps. We create a pandas data frame with 2 columns, profit and loss in dollars, and sentiment score. Both columns contain negative values, positive values, and zeros, giving a small dataset for demonstrating max absolute scaling. This setup shows how the scaling handles values on both sides of 0, while leaving zeros unchanged. The code first verifies that the original data has the expected shape of 5 rows and 2 columns. If it does not, it raises an error to signal the mismatch. This early check helps ensure the data is structured correctly before the rest of the process runs. MaxAbsScaler scales each feature by its largest absolute value, keeping signs and 0 values unchanged, while bringing magnitudes into the range from -1 to 1. Applying its fit and transform process calculates those maximum values from the original data and uses them to rescale each feature independently. The result preserves the data's overall structure, while putting feature values on a comparable scale. After scaling the data, we convert it back into a pandas data frame, so the columns can be clearly labeled. The new column names identify the scaled profit loss and scaled sentiment values, preserving the data structure while making the transformed features easier to interpret. The original and scaled data are combined side by side, so their values can be compared easily. The scaled values are rounded to 2 decimal places for readability, and the final combined table is printed without row indices to keep the output clean and focused. We show the maximum absolute value used to scale each feature with the MaxAbsScaler. These values are taken from the scalar's stored maximum absolute values, rounded to 2 decimal places, converted into a list, and printed for easy review. The code checks whether 0 values stayed unchanged after scaling, by counting how many entries in the scaled data are still 0. It converts this count to an integer, and prints the result, confirming that the scaling process preserved the zeros as expected. This example shows how max absolute scaling prepares signed data for machine learning. Each feature is scaled independently by its largest absolute value, which reduces magnitudes while keeping signs and zeros unchanged. The output compares the original and scaled values and reports the scaling values used, helping show how features with different ranges can be put on a more consistent scale. Robust transforming. Robust scaling. Robust scaling helps prepare numerical features that have outliers, skew, or heavy tails. Instead of using the mean and standard deviation, it centers values around the median and scales them using the interquartile range. This keeps extreme values from dominating the scale, so typical observations remain easier for a model to learn from. Robust scaling changes a feature's center and spread without changing the overall shape of its distribution, so skewed data remains skewed. In contrast, quantile transformations reshape values to follow a chosen distribution, while power transformations try to make skewed data more symmetric. Robust scaling is the more conservative choice when you want to preserve the original order and meaningful size differences, while reducing the influence of outliers. Robust scaling is useful for skewed numerical features with real outliers that should not be removed. It reduces the influence of extreme values while keeping meaningful information, which helps scale sensitive algorithms such as distance-based or gradient-based methods. If the main problem is strong asymmetry, a power transformation may be better, while rank-based comparisons may call for a quantile transformation. The key choice is whether the feature needs resistant rescaling or a change in shape. Python code. Robust scaling. This section shows how robust scaling handles skewed purchase amounts, especially when extreme values are present. It compares conservative scaling, which limits the influence of outliers, with methods that reshape the distribution more strongly. The goal is to see how outliers change transformed feature values, and why the choice of scaling method matters. We import key Python libraries for data analysis and preprocessing. NumPy supports numerical work, pandas organizes structured data, and Matplotlib creates visualizations. From Scikit-Learn, we use scaling and transformation tools to handle outliers, reshape feature distributions, reduce skewness, and make data more suitable for modeling. We create a NumPy array of purchase amounts that is deliberately skewed, with a few much larger values acting as realistic outliers. The values are stored as floats, so later scaling transformations can be applied properly. This setup helps show how different scaling methods respond to skewed data and extreme values. The code first validates that the purchase amounts are a one-dimensional numeric array with at least 5 values. If the data does not meet these requirements, it raises an error explaining the expected format. This check helps prevent problems during later scaling and transformation steps. Before transforming purchase amounts, reshape the one-dimensional data into a two-dimensional column format. This is needed because Scikit-Learn transformers expect a feature matrix, making the data compatible with later scaling and transformation steps. Robust scaling is applied to purchase amounts to reduce the impact of outliers while keeping the overall shape of the data. Using Scikit-Learn's RobustScaler, the purchase amounts are reshaped into the required two-dimensional format, transformed, and then flattened back into a one-dimensional array. This produces more stable scaled values when extreme purchases are present. The code uses a QuantileTransformer to convert purchase amounts according to their ranks, mapping them onto a normal distribution. It sets the number of quantiles to match the number of values so each amount gets its own rank, and uses a fixed random state for reproducibility. The data is reshaped for fitting, transformed, and then flattened back into a one-dimensional array for easier use. A power transformation is used to reduce skewness in purchase amount data. The Yeo-Johnson method is chosen because it can handle zero and negative values, and standardization makes the transformed data have zero mean and unit variance. After fitting and transforming the reshaped data, the results are flattened back into a one-dimensional form. A pandas data frame is used to compare original purchase amounts with values transformed by several scaling methods. Robust scaling reduces the influence of outliers by using the median and interquartile range. Quantile transformation reshapes values toward a normal distribution based on rank, and power transformation helps reduce skewness. This makes it easier to see how each method treats both typical and extreme purchase amounts. The code makes the output easier for beginners by selecting a few specific rows from the summary data, rounding their values to 2 decimal places, and printing them with a clear label. It then displays the selected transformed purchase amounts as readable text without row indexes. A plot is created to compare original purchase amounts with 3 transformed versions of the data. The original values are plotted against robust scaling, quantile normal transformation, and power transformation, using the same marker style for easy comparison. Together, these lines show how each method changes the scale or distribution of the original data. The plot is prepared to compare robust scaling with distribution reshaping. Its title and axis labels clarify that the horizontal axis shows original purchase amounts, while the vertical axis shows transformed values. A legend identifies each transformation method, and the plot is then displayed so the effects of the scaling methods can be compared visually. This script compares how robust scaling, quantile transformation, and power transformation handle skewed purchase amounts with outliers. Robust scaling reduces the influence of extreme values without changing the overall shape. Quantile transformation reshapes values by rank toward a normal distribution. Power transformation smooths out skewness. The output and visual comparison show how each method changes typical and extreme values, as well as the data's overall scale and distribution. Sample normalization. Sample normalization adjusts each observation, or row, rather than standardizing each feature column. Its goal is to compare the internal pattern of values within a sample, not the sample's overall size. In document classification, for example, it helps prevent longer articles from appearing more important simply because they contain more words. This makes it useful when relative composition matters more than absolute magnitude. Sample normalization, quantile transformations, and power transformations solve different scaling problems. Quantile and power transformations mainly reshape skewed feature distributions, while sample normalization controls the overall scale of each sample. This is useful when proportions matter more than total size, such as comparing how customers divide spending across categories. Sample normalization changes how data should be interpreted, so it is most useful when you care about relative composition, rather than absolute size. It helps compare internal patterns in fields like text mining or genomics, where samples may differ in length or intensity. But it can remove important predictive information, such as total transaction amount in fraud detection. For skewed data, first decide whether the skew reflects meaningful signal or just size differences. Use sample normalization for comparing patterns and other transformations when the goal is to adjust the distribution itself. Python code. Sample normalization. Row normalization rescales each observation as a whole, rather than transforming individual features. This changes the magnitude of each row profile, making the comparison focus on the normalized observation patterns. We import key Python libraries for data preparation and analysis. NumPy supports numerical work with arrays, while pandas helps manage and analyze tabular data. From Scikit-Learn, the normalizer scales each sample to unit length, the PowerTransformer reduces skewness and stabilizes variance, and the QuantileTransformer reshapes features toward a uniform or normal distribution. A two-dimensional NumPy array is created to store customer spending profiles. Each row represents one customer, and the three values in that row represent different spending categories. The array uses floating point numbers, so later calculations can be handled with appropriate precision. Before transforming the data, the code verifies that the spending data has 4 rows and 3 columns, representing 4 customer profiles with 3 spending categories each. If the shape is different, it raises an error to signal an unexpected format. This check helps prevent problems in later transformations. We use Scikit-Learn's Normalizer with the L2 norm to scale each customer's spending row to a length of 1. This turns each spending profile into a unit vector, so comparisons focus on the pattern or direction of spending, rather than the total amount spent. The code prepares the data for machine learning by applying 2 normalization steps. First, a QuantileTransformer reshapes each feature across customers using 4 quantiles and maps the output to a normal distribution, with a fixed random state for reproducible results. Then, a PowerTransformer uses the Yeo-Johnson method and standardization to make the data more Gaussian-like, with zero mean and unit variance. The code transforms the spending data to make its features more Gaussian-like before analysis or modeling. It first uses a quantile transformation with 4 quantiles, then applies the Yeo-Johnson power transformation, which can stabilize variance and works even when values are not strictly positive. Both methods are fitted to the data and used to create transformed versions for later use. We create a pandas data frame to compare row magnitudes before and after several data transformations. Using NumPy's norm calculation, we measure the original row lengths, then compare them with the lengths after sample normalization, quantile transformation, and power transformation. This makes it easy to see how each method changes the scale and distribution of the rows. The code gives the summary rows meaningful labels based on customer spending profiles, making the results easier to interpret. It also rounds the numerical values to 2 decimal places, creating a cleaner output that is easier to compare. The output explains that comparing row magnitudes shows how sample normalization controls the size of each row. It then displays a summary of row magnitudes before and after the transformations, making it easier to see how each transformation changes the data. This script compares how normalization and transformation methods change customer spending data. After checking the data shape, it uses sample normalization to scale each customer's spending profile to the same overall length. It also applies quantile and power transformations, which make feature distributions more normal-like, but do not control each row's magnitude. The final comparison shows that sample normalization changes row size directly, while the other methods mainly reshape the data distribution. Sparse, safe scaling. Sparse, safe scaling transforms numerical features without changing zero entries into non-zero values. This matters for sparse datasets, where zeros often represent absence or no interaction. If a transformation makes the data dense, it can greatly increase memory use and computation time. So, any scaling method should be checked to ensure it preserves the sparse structure. For skewed numerical features, choose transformations that respect both the data's meaning and how it is stored. Quantile transformations can reshape distributions, but may treat zeros in ways that distort sparse data. Power transformations can reduce skewness, but they may also require changes that break sparsity. The key is to avoid improving the distribution's appearance at the cost of damaging the data structure. Sparse safe scaling preserves zeros by avoiding mean subtraction, which can turn zero entries into non-zero values and break sparsity. A common approach is to scale by a maximum absolute value, so feature sizes are adjusted while zeros stay unchanged. For highly skewed data, transform only the non-zero values or separate occurrence from magnitude, keeping zeros meaningful while making positive values easier for models to learn from. Python code, sparse, safe scaling. This example highlights scaling choices that are safe for sparse data. Multiplicative scaling keeps meaningful zero values intact, while centering and quantile transforms can turn sparse data into dense data. We import tools for numerical work, visualization, and feature scaling. NumPy handles arrays, while Matplotlib supports plotting. From Scikit-Learn, MaxAbsScaler scales values by their largest absolute value while preserving sparsity. RobustScaler reduces the effect of outliers using the median and interquartile range. And QuantileTransformer reshapes features toward a uniform or normal distribution. We create a small NumPy array of event counts, with customers as rows and rare event counts as columns. Its mix of zeros and small floating point values simulates sparse data, making it useful for testing how scaling methods affect sparsity. The code first verifies that the counts array has 5 rows and 3 columns, matching the expected data format. If it does not, it raises an error to signal that the input is invalid. This early check helps protect data integrity and prevents later processing problems. The code counts how many entries in the counts array are non-zero, using NumPy's count_non-zero function. This gives a baseline measure of the data's sparsity before scaling, so later results can show whether different scaling methods change that sparsity. We apply MaxAbsScaler to the count data to scale each column by its largest absolute value. This keeps zero values unchanged, so the data remains sparse. Counting the non-zero entries afterward confirms that the scaling preserved the original sparsity. We use Scikit-Learn's RobustScaler to transform the count data by subtracting each feature's median. This centering can turn some zero values into non-zero values, reducing sparsity. After the transformation, we count the non-zero entries to see how much the data's sparsity has changed. A QuantileTransformer is used to reshape the counts data into a normal distribution using 5 quantiles with a fixed random state for reproducibility. After transforming the data, the non-zero entries are counted, with values rounded to 12 decimal places for accuracy. This shows how the transformation can affect sparsity, including whether zeros become non-zero values. We compare how several scaling methods affect sparsity by counting non-zero entries before and after each transformation. Max absolute scaling preserves zeros because it only rescales values, while robust scaling with centering can turn zeros into non-zero values by subtracting medians. The quantile transformation can also change zero entries by reshaping the data distribution, so we check its non-zero count and inspect the rounded transform values of the first feature. The code compares several scaling methods by recording how many data entries remain non-zero after each transformation. It stores these counts for the original data and for the MaxAbs, robust, and quantile scaling methods. This makes it easier to see how each method affects the sparsity of the dataset. This code creates a bar chart to compare how different data transformations affect sparsity. It plots each transformation method on the x-axis and the number of non-zero entries on the y-axis, using distinct colors for clarity. The chart is titled and labeled to show that it measures how many values become non-zero, with the y-axis scaled to the total number of elements before displaying the plot. This script compares how scaling methods affect sparsity in rare event count data. Max absolute scaling keeps the number of non-zero values the same, so it preserves sparsity. Robust scaling and quantile transformation increase the number of non-zero values, making the data denser. The main takeaway is that max absolute scaling is better suited when preserving sparsity is important. Distribution shape. Quantile mapping. Quantile mapping transforms a numerical feature by using each value's rank in the distribution, rather than its distance from the mean. It is useful for skewed data, long tails, or clustered values, where standard scaling can still be affected by extreme values. By spreading low, middle, and high-ranked values across a chosen target distribution, such as uniform or bell-shaped, it creates a more balanced feature representation. When using quantile mapping, first consider whether the data is dense or sparse. It often works well for dense data, such as sensor readings, because reshaping the distribution can help models use meaningful value patterns. For sparse data, be careful, since zeros may represent absence, and quantile mapping can turn them into non-zero values, increasing memory use and changing their meaning. In these cases, decide whether preserving zeros matters more than adjusting the distribution. Use quantile mapping when reshaping a skewed, dense feature is more important than preserving exact zeros. It can reduce outlier effects and make values more uniform, but it may be a poor fit for sparse features where zeros carry meaning. In those cases, keep zeros intact or separate absence indicators from continuous values before transforming. For example, it may help with total customer spending, while product category indicators should remain sparse. Python code. Quantile mapping. This example compares dense and sparse quantile mapping. It shows how quantile mapping reshapes ranked values to match a target distribution, while highlighting when sparsity is maintained. This setup imports key tools for numerical processing and data scaling. NumPy supports random number generation and array operations, while the QuantileTransformer reshapes data by mapping quantiles to a chosen distribution. The maximum absolute scaler rescales values using their largest absolute value, while keeping zero entries unchanged, which helps preserve sparse data. The example uses a fixed random seed of 42. So the results are reproducible each time it runs. It then creates 200 values from a log normal distribution, with mean 3 and standard deviation 1, producing skewed, varied data that resembles dense real-world spending patterns. Create an array of 200 zeros to represent a mostly empty feature. Then replace the first 20 values with random integers from 1 to 7. Producing a simple example of sparse-like data, with only a small number of non-zero entries. A QuantileTransformer is configured to map each feature into a uniform distribution from 0 to 1. Using 50 quantiles divides the data into 50 equal groups, while a fixed random state makes the results reproducible. This helps apply quantile mapping consistently across features with different original distributions. We initialize Scikit-Learn's MaxAbsScaler to prepare data for scaling. It rescales values based on the largest absolute value, so the data falls between -1 and 1, while keeping zeros unchanged. This makes it especially useful for sparse data, where zero entries are meaningful. The code uses quantile mapping to transform dense spending data into a more uniform distribution. It first reshapes the data so the transformer can process it, then applies the quantile transformation to spread skewed values evenly by rank. The result is flattened back into a one-dimensional form for later use. The sparse counts are reshaped into 2 dimensions so the quantile transformer can process them. The transformer adjusts their distribution toward a uniform shape, which may change some zero values into non-zero values. The result is then flattened back into one dimension for later use. MaxAbsScaling rescales each feature in the sparse counts array by its largest absolute value, while keeping zero entries unchanged. The data is temporarily reshaped into 2 dimensions so the scaler can process it, then flatten back to 1 dimension to preserve the original structure and zero pattern. First, verify that the transformed dense quantiles have the same number of data points as the original dense spending data. This confirms the transformation preserved data integrity. If the lengths differ, an error is raised to signal that data may have been lost or added during the process. The process checks that the transformed sparse quantiles have the same number of data points as the original sparse counts. If the lengths differ, it raises an error to indicate a problem in the transformation. This safeguard helps preserve data integrity and prevents incorrect analysis from unexpected changes in data size. We compare the number of non-zero entries before and after scaling to see how sparsity changes. The original sparse counts provide the baseline. Quantile mapping shows how many values become non-zero, and MaxAbsScaling shows whether the original sparsity pattern is preserved. Before transforming the dense spending data, we print a brief summary of its distribution. The minimum, median, and maximum are calculated and shown to 1 decimal place, giving a quick baseline before quantile mapping. This line summarizes the dense spending data after quantile mapping by reporting the minimum, median, and maximum transformed values. It formats each value to 2 decimal places, giving a quick view of how the distribution changed after the transformation. This line reports how many non-zero values are in the feature before scaling. It inserts the stored count into a console message, giving a quick view of the data's initial state before any transformation. This line reports how many entries remain non-zero after quantile mapping. It shows the count out of 200 entries, helping illustrate how the transformation affects the data's sparsity. This line reports how many values remain non-zero after MaxAbsScaling. The key point is that this scaling method keeps zero values unchanged, so the feature's original sparsity pattern is preserved. The key point is that quantile mapping works well for dense, skewed features whose values are unevenly distributed across a wide range. It is not a good choice for features with structural zeros, where 0 represents a meaningful absence rather than a low value. This helps choose the right transformation based on the data's structure. This script compares quantile mapping on dense and sparse data. For dense, skewed spending data, quantile mapping spreads values evenly by rank and produces a uniform distribution. But for sparse data with many structural zeros, it can change zeros into non-zero values and destroy the sparsity pattern. Max absolute scaling is better for sparse features because it preserves zero entries while still rescaling the data. PowerTransform. A PowerTransform reshapes numerical data to make skewed distributions more balanced. It is especially useful when large values dominate the data, because it reduces the influence of extremes while keeping the original order of values. This can help statistical and machine learning models work more effectively. When choosing a PowerTransform, first consider whether the data is dense or sparse. Dense data usually works well because the transform does not greatly affect storage. Sparse data has many zeros that often mean absence, and a transform can turn those zeros into non-zero values, destroying sparsity. This can greatly increase memory use and slow training, even if the transformed data has a better distribution. Choose a PowerTransform based on both your modeling goal and the structure of the data. It is most useful for dense, positively skewed features, but the transform must also handle zeros or negative values when they are present. Check the data before and after transformation to make sure values remain meaningful, sparsity is preserved, and the choice supports model performance without unnecessary storage or computational cost. Python code. PowerTransform. This example contrasts preprocessing for dense and sparse data. PowerTransforms can help reshape skewed, dense numerical features, while zeros in sparse data should usually be kept as zeros. We import key Python tools for data processing and visualization: NumPy for numerical work with arrays and matrices, and Matplotlib's plotting module for creating visualizations. From Scikit-Learn, we also import a power transformation tool to make data more Gaussian-like, and a maximum absolute value scaler to rescale sparse data while preserving its sparsity. A fixed random seed is used to make the results reproducible. Then 300 feature values are generated from a log normal distribution, with mean 2 and standard deviation 1. This creates skewed data, which is useful for showing how power transforms can reshape a distribution. To create a sparse count feature, start with an array of 300 zeros so most entries have no value. Then randomly choose 30 unique positions and fill them with random integers from 1 to 7. This produces a mostly zero array with a small number of meaningful non-zero counts. The process first checks that the dense amounts array and the sparse counts array have the same number of rows. If they do not match, it raises a value error to stop processing. This validation ensures the data is aligned before any later transformations occur. The data is first reshaped into a two-dimensional form, so the power transformer can process it. A Yeo-Johnson transformation is then applied, which works with zero or negative values and standardizes the data by default. This reduces skewness and makes the distribution more normal, after which the result is flattened back into a one-dimensional array for later analysis or visualization. The sparse counts are first reshaped into a single-column matrix, so the scaler can process them. A maximum absolute value scaler is then used because it works well with sparse data and keeps zero values unchanged. After scaling, the transformed result is flattened back into a one-dimensional array for easier use later. We compare the number of zeros before and after applying the MaxAbsScaler. If the zero count stays the same, the scaling has preserved the sparse structure of the data. We compare key values before and after preprocessing to understand each transformation. For dense data, checking skewness before a power transform and the mean afterward shows how the transform changes the distribution. For sparse style data, counting zeros before and after MaxAbsScaling confirms that the zeros are preserved. The main lesson is that power transforms can reduce skewness in dense features, while MaxAbsScaling is better suited for sparse data where zeros are meaningful. This plot compares the distribution of the original dense feature values with the values after a power transform. Both are shown as overlapping histograms with the same bin count and transparency, making it easier to see how the transformation changes the shape of the data. The chart includes clear axis labels, a title, and a legend to distinguish the two distributions. This example shows how to pre-process different numerical features based on their structure. A skewed dense feature is transformed with the Yeo-Johnson PowerTransform to reduce skewness and standardize its values. A sparse feature with many zeros is scaled with MaxAbsScaler, which keeps the zeros unchanged and preserves sparsity. The main lesson is to use power transforms for skewed dense data and zero-preserving scaling for sparse data. Distribution comparison. Choose a distribution transformation by matching your data's current shape to what your model needs. Quantile mapping reshapes values by rank to fit a target distribution, such as normal or uniform, making it useful for skewed or heavy-tailed data. Power transformation makes a smoother adjustment that reduces skewness and stabilizes variance while preserving the original order of values. When choosing between quantile mapping and power transformations, first, consider whether the data is dense or sparse. Dense data can usually tolerate transformations that change many values, but sparse data often has meaningful zeros. If a transformation turns zeros into non-zero values, it can destroy sparsity, use more memory, and slow training. To avoid this, use methods that keep zeros unchanged, such as max absolute scaling, or apply stronger transformations only to dense columns. Choose distribution transformations based on how they affect the full modeling process, not just whether the feature looks more normal. Quantile mapping can reduce extreme values and help distance-based or smooth models, but it may hide original differences. Power transformations reduce skew while keeping more connection to the original scale, though they may struggle with zeros or severe irregularities. The best choice should handle zeros properly, consider computational cost, and improve model performance while preserving the data's structure. Python code. Distribution comparison. Compare dense and sparse scaling by focusing on whether sparsity is preserved. Some distribution transforms can turn stored zeros into non-zero values, which changes the structure of the data. The key takeaway is to choose scaling methods that maintain sparsity when that property matters. This setup imports key tools for numerical work, visualization, and data preprocessing. NumPy supports array and matrix operations, while Matplotlib helps create plots. From Scikit-Learn, MaxAbsScaler, QuantileTransformer, and PowerTransformer provide different ways to scale or transform data, often to improve normalization and machine learning performance. We create a NumPy array to represent a sparse feature, with several zero values followed by larger spending amounts. This column of 8 values helps demonstrate how different transformations handle sparse data, especially whether they preserve or change the zeros. Before transforming the data, the code verifies that the spending array has the expected shape of 8 rows and 1 column. If it does not, it raises an error to stop processing. This check helps ensure the data is correctly formatted and prevents problems during later transformations. The spending data is transformed in 3 ways to adjust its scale and distribution. Max absolute scaling rescales each feature while keeping zero values unchanged, so sparsity is preserved. A quantile transformation then maps the data toward a normal distribution, which may spread out zeros and reduce sparsity. Finally, a Yeo-Johnson power transformation makes the data more Gaussian-like and can further change its distribution and sparsity. We count how many values are exactly zero before and after applying different data transformations. Comparing the original data with results from MaxAbsScaler, QuantileTransformer, and PowerTransformer shows whether each method preserves or changes zero values. These zero counts help reveal how the transformations affect sparsity in the spending data. The output compares how many zero values remain after different scaling transformations. It shows the original zero count, then the counts after MaxAbsScaler, QuantileTransformer with a normal output, and PowerTransformer. The key takeaway is that MaxAbsScaler usually preserves zeros, while distribution shaping transformations often turn them into non-zero values. Create a scatter plot to compare the original spending values with three transformed versions: MaxAbsScaling, quantile normalization, and power transformation. Plotting them together shows how each method changes the data and helps reveal whether it preserves or alters sparsity. The plot is set up to compare how different transformations affect spending data. Its title states the focus on transformation behavior and sparsity preservation, while the axes show original spending amounts against transformed values. A legend identifies each method, and the plot is displayed so the transformations can be visually compared. This script compares how scaling methods affect a sparse spending dataset with many zero values. Max absolute scaling keeps the zeros unchanged and preserves sparsity, while quantile and power transformations tend to turn zeros into non-zero values, making the data denser. By counting zeros before and after each transformation and plotting the results, the script shows that max absolute scaling is the best choice when maintaining sparsity is important. In this lecture, you learned to apply standard, min-max, max-absolute, robust, and sample normalization transformations. Compare quantile and power transformations for skewed numerical features. And choose scaling strategies that respect sparse and dense data constraints. In the next lecture, Lecture B, we will go over expansion binning.
Thank you for your attention. See you all in the next lecture.